Hello, everyone. How are you? There we go. Everyone hear me? Can anyone hear me?
Yeah, I can hear you.
All right. How many folks do we? Who's going to keep up on the chat for me?
I can try, but
Okay. Thank
it's not
you.
that much.
It's not that much activity yet. Oh,
I'll try to help out, Matt.
all right. We've got a helper here. I don't know how much help you're going to be, Jerome, but he's been wanting to help all morning, haven't you? Yeah. There you go. Okay. So I realize this is probably going to be a lot of this is new for some of the most folks, but some of it we've covered in the lab and from last week, and will be actually one of the questions in the recitation is pretty much exactly what you're going to be doing in the lab this week. So I figured it was a good place to start. That's basically why I skipped the gas laws chapter and went right into thermochemistry, since we're actually doing thermochemistry in the lab. So you can see that the first question here is basically precisely what you did last week in the lab. So I'm assuming that most people are going to be able to answer that question. If you can't, let me know, because I was just going to go to the second one, because the second one is basically this same question, but with a little bit of a twist on it. Okay, so the second one is you're basically doing the same sort of calorimeter measurement, but in this instance, the heat capacity of the calorimeter itself needs to be taken into consideration. So, all right, see you, Jerome. So, what this means is, like, if we did the lab from last week in the real world, in the actual lab, one of the calculations you would have had to have done is figure out how much heat is absorbed by the styrofoam cup, because obviously not all of the heat is going to go from the metal that you put in the water right into the water. Some of it's going to be lost. Some of it's going to be lost into the walls of the container of the styrofoam cup. Some of it's going to be lost into the air. And so to get an accurate measurement of how much heat is gained by the water, you also need to figure out how much heat is lost into the surroundings. And this question takes that into consideration. So what we need to figure out in this one is how much heat is gained by the calorimeter. So let me see if I can get my pen up here going again. Oh, annotate. There we go. All right, see if I can draw on this thing. So the information we have is we've got, we know the mass of the unknown mineral. We're trying to calculate the heat capacity of. We know what the initial temperature of the water is. The initial temperature of the water is 23.6 degrees. The initial temperature of the metal, or the mineral in this instance, before we put it into the water, was 98.7. And then we know that when the two things balanced out, and the temperature of the water and the temperature of the mineral were the same, and that's when we want to stop the reaction then and measure that temperature, is 32.4 degrees. So the information that we have that we don't have, but that we know, is that we need to know what the heat capacity of the water. We know what that number is. But the other heat capacity we need to figure out was the calorimeter. Now here that's given to you. So what we need to do is determine Q of the mineral, and that's going to equal Q of the water plus the heat that goes into the calorimeter. Okay, so there's two places where that heat goes. And right now, so far, all we've been considering is the heat of the water, with the assumption that the calorimeter is not going to change temperature. Well, for like a real fancy bomb calorimeter or something like that, even something like that is going to absorb some heat, some small amount of heat. And the amount of heat that absorbs is right here. So basically what that says is for every increase of temperature, 1 degree Celsius or 1 Kelvin, 15.7 joules of energy from the reaction is going to get lost into the calorimeter. So we need to figure that out. So we have two things to calculate. And the first one, we figure out Q of the water, which is the mass of the water, times the specific heat of the water, times the change in temperature, right? And for the calorimeter, it's the same thing, except here we don't consider the mass, because the mass of the calorimeter is not important. What's important is how much energy does the whole thing absorb. And we would have calculated that if some of you actually like read the old lab manual for that particular test. The way we would have done that is by adding a constant volume of hot water and a constant volume of cold water, mixing them together. And then you would calculate if it was a perfect world, the temperature should balance right in the middle between the two. And you find out that it doesn't. It's actually a little bit lower than that. And the difference between the amount of energy that it would have, the amount of heat that it would have had if it didn't lose any, would be the calculated. And then you would see how much energy it actually lost into the calorimeter. So here that was done for us. Is there a question? I saw the chat light up. Is there a question so far?
Are the recordings for class on Canvas?
Excuse me?
Are the recordings on are the recordings for class on Canvas?
Yes. Yes. Oh no, Canvas? No, they're on YouTube. I'm putting them on YouTube, and there's a link. I put a link on the announcements to the YouTube page. So were you aware that there was a YouTube page?
Trying to gain subscribers.
No, I just wanted to put it somewhere. So yeah, I mean, Zoom records these things, and so yeah, what I've been doing is just putting them on. I set up a YouTube page, Chem 210 JF LeBlanc, and I've been putting them there. I put an announcement in, I think yesterday, with the link. These are going into the recitations and the labs. Yeah, it's not like I'm looking for advertisers or anything. No, just wanted to have that there in case you missed them. All right, so we got two things to calculate. We got the heat goes into the water and the heat that goes into the calorimeter. So the heat that goes into the calorimeter, since we don't have we're not worried about a mass, all we do is have the heat capacity times the change in temperature. And so the heat capacity of the calorimeter is given there, it's 15.7. So that is 15.7 joule Kelvin times the change in temperature. For the water, 72.4 grams times 4.184 joules per gram Kelvin times delta T. So, times delta T. So the question is, so what is delta T for the water and the calorimeter? Someone calculate that for me. Someone's got to have a calculator. Excuse me. So what's the change in temperature of the change in temperature of the water and the calorimeter should be the same. What's the change in temperature for them? Is everyone muted or?
It's not
8.8.
8.8.
Yes, 8.8. Mm-hmm. Yeah, so the change in temperature is from 32.4 from 23.6 to 32.4. So that's 8.8. So 8.8 K times 72.4 grams times 4.184 plus 15.7 times 8.8 K. Let me erase some of this at the bottom. We can put some numbers in here. All right, so you can see that the change from the change in heat of the calorimeter is not going to be a lot, which is what you want. I mean, you don't want a lot of the heat to get lost into the calorimeter, but there is a small amount and we need to take that into consideration. So let's start doing our calculation. So what would be the amount of heat and number of joules going into the water?
Can you repeat that question?
How much heat is going into the water? So this is the water. Oops. This is the water here. So this part of the equation is the water. And this part of the equation is the calorimeter. So how much heat goes into the water, is gained by the water?
That's just multiplying it all together, right?
Mm-hmm.
Yep, I got 2,665.71.
Yep. So 2,665.7 joules. Then how much goes into the calorimeter?
138.16.
138.2. All right, so our total 138.2 is 2,803.9 joules. So that is equal to our Q mineral. So for our Q mineral, that is 307 grams times C, which is the heat capacity, which we haven't figured out, times the change in heat of the mineral. So what's the change in temperature, the delta T for the mineral?
$66.3.
Right. So it's gone down from 98.7 when you put it in. So obviously it was boiled in like hot water and then pulled out and then put into the water. So it's gone down in temperature from 98.7 to 32.4. So it's 66.3 K. So to get our mineral, we just basically divide 2,803.9 joules and then divide that by 307 grams times 66.3 Kelvin. So let me erase this so we can get the units right.
How did you get 307 again?
307 is the number of grams of the unknown mineral right there.
Oh, my bad. I didn't see it.
Yeah. So our answer is 2803.9 joules. So that's why I like to include the units, because I know that heat capacity should be in joules divided by grams Kelvin. And then when we look at this expression here, we can see that it is in joules on top divided by grams Kelvin. So more than likely, if we did the calculations right, at least we have the units right. So we know we probably are on the road to the right answer. So what do we get for 2803.9 divided by 307 times 66.3?
I got 0.1377.
Okay.
Wouldn't it be 0.138 since we're
Let me-
it's three
let me
Two,
double-
significant.
yeah. 3.
307 divided by 66.3. Yeah, so let's see, how many, so we should have
Three?
three significant digits, right? We have three significant digits in our mass, three significant digits in our temperature, three significant digits in the heat capacity of the calorimeter. So yeah, we should have three significant digits. So it should be 0.138, and then check the units, joules per gram Kelvin. So right to me. Final answer here. Okay, so basically the same, just doing this the same sort of calculation. The only difference is we need to take into consideration what the calorimeter's heat capacity is, and that's it. That's the only difference. All right. So let's. Unfortunately, I need to erase all of this. It should be there in the when we look at the tape, at the recording, but I need to get rid of it to go to the next. I should put these on slides. That's what I'll do next time. I'll just put these on slides. A question per slide. That makes a lot more. That'll make it a lot easier.
And the only difference between this question and the first one is you take, in fact, the temperature of the calorimeter, right?
Right. Yeah. The first question. It even says there that we assume that no heat is absorbed by the calorimeter. Now that doesn't happen. The calorimeter is made of material, and it's going to heat up very slightly. You can see that the difference was, I think it was only about 1% of the total amount of heat went into the calorimeter. But in order to be accurate, you would need to consider that. And when chemists do these sorts of reactions with like a bomb calorimeter, that is built in. That the heat capacity of that calorimeter they're using is basically a constant, and so that is already baked into the calculations for the heat capacity. All right, so now here, number 3, that's a reaction where we're now dealing with heat as a part of a chemical reaction. We just need to include it. And people have probably heard of thermite, right? If you've watched any Mythbusters, you've seen thermite before. Have you ever seen thermite reactions? They're really cool because they produce a tremendous amount of heat. Basically, just things get molten in a hurry. And that reaction goes because aluminum really likes to donate electrons to iron. So you have aluminum, and aluminum is much more stable as a +3 ion, and than it is as just aluminum. And so it donates 3 electrons to iron to turn it back into elemental iron, and it basically just releases tremendous amount of heat. It basically will melt anything. And so, as you can see here, it welds like steel rails together. So it, it does a really good job of releasing heat. So to do this, meaning it is highly exothermic. So this delta H, what delta H means in this regard is it's delta H for the reaction. And it's, so let me get a, so delta H is released for this particular reaction. And so if 2 moles, excuse me, if 2 moles of solid aluminum react with 1 mole of iron 3 oxide, then 850 kilojoules of heat is released. So what we need to do is figure out if 725 kilojoules of heat are released, how much iron is that? So let's go. So we treat this as we would any other part of the reaction. So for basically what it's saying is that for every 2 moles of iron that's produced, every 2 moles of iron that's produced, 850 kilojoules of energy are released, okay? So if 725 kilojoules of energy are released, that would be equivalent to 2 moles. 2 moles, we have 850. So we just multiply these two. That subtracts, that gets rid of kilojoules, and we're left with moles of iron. So how many moles of iron are we talking about here?
Well, sorry, 1.70 or 71. Sorry.
Yeah, carry as many significant digits as you want at this point. So I would just say 1.706, say, moles of iron. But that's not the question, right? The question is what mass of iron is formed. So we're not quite done. So what would be our next step?
Go from moles to grams.
Right. And how do we, so we have our 1.706 moles of iron. And what do we multiply that by to get grams of
The
iron?
molar mass of iron.
Mm-hmm. And would we put the molar mass on top or on the bottom?
The numerator.
Right, numerator. So has anybody got their periodic table open?
It's 55.845.
55,825. That sounds about right. 825?
845.
845. So 1.706 times 50 times 50 or 55?
55. I can verify that.
50. Man, my writing with this thing is horrific. Yes, that is a 55, if you can believe that. All right, so what's my total number of grams?
Sorry, what was the
I got 1.706 moles of iron. And I've got at 55.845 grams per mole.
I got the mass 98.29 gram.
8?
No, 98. Sorry, 98.
I got 95.
Mm,
So I probably got the number wrong. Is it 55.845?
Oh wait, no, I got the number wrong. Sorry.
Well, I can't believe you couldn't make out a 5 from my perfect writing here.
No, I was Yeah, you're right.
So what is it? It's 90
95 point
point
22.
27.
6. Close enough. Yeah, so it should be 3. So there's 3 significant digits for the heat here. There's only 2 here. So you would be right with either 95 grams or 95.3. I wouldn't, either one would be. So you see how that works. So when we give a delta H, when you see delta H reaction, what that usually means is per mole. But in this particular, we've got 2 moles of aluminum going to 2 moles of iron, and their oxides are 1 mole each. And so when you have that sort of situation, you just say for the whole reaction, delta H is this much. Generally, if you're forming like 1 mole of product, you just say delta H and then you give reaction like this. And there's an example coming up in a minute. So then any questions about that one, how we get to there? Basically, we're just treating the heat like we would any other part of the reaction. If there's so much so if it's an exothermic reaction, heat is a product, and we need to use that to do our balancing. If it's an endothermic reaction, then the heat will be going into the reaction here, and so the heat would be on the left side. It would be a reactant rather than a product. So the questions about how to treat heat as a product or reactant, balancing these equations. Okay. All right, let me erase. Oh, clear. All right, so let's go to. So yeah, let's just do this, because this is basically what you're going to be doing in your lab this week. So you're going to be doing a neutralization reaction, but you're going to be doing it in a variety of different ways. First, you're going to measure the heat of First, you're going to do a reaction of taking sodium hydroxide, solid, and then plus water. And that will give us sodium ions, hydroxide ions in aqueous solution. That is an exothermic reaction. When we break the ionic bond here and then replace them, who is here for lecture this morning? You remembered what causes the release of heat? The formation of bonds or the breakage of bonds?
Formation.
Formation.
Right, formation. So in this instance, we're breaking an ionic bond, but what are we replacing them with? Because if all we were doing was breaking this ionic bond, it would take heat to do that. It would be an endothermic reaction. But this is an exothermic reaction. So what bonds do you think are being formed? Give you a sec to think about that. It's a little tricky because it's actually not present here. I mean, it actually is. When I put aqueous here, that might give you a hint. Anybody have any ideas?
Is it hydrogen gas?
No, we're producing hydrogen gas. No, we're producing sodium ions and we're producing hydroxide ions. That's all we're doing. But something else is happening when we make those. What do you think? What else is happening?
In the chat, it says exothermic reaction.
It is an exothermic reaction, but my question is why? What bonds are being produced on this side of the reaction?
Ionic bond.
No, we actually broke the ionic bond. That took in.
Covalent.
What was that? Somebody had a guess there. What was it? Let's just brainstorm. Just throw things out.
I have a question.
Okay.
So what happened? What happened to HCl?
Oh, we're just here. I'm just dealing with this. This is the first reaction you're going to do in your lab on Thursday. I'm just talking about that first. So you're going to do 3 reactions. You're going to do solid sodium hydroxide in water. One is going to be looking at solid sodium hydroxide plus liquid HCl. And the third one, you're going to be looking at a solution of sodium hydroxide plus a solution of HCl. You'll look at the amount of heat produced by each one of those reactions. This is the first reaction. It is an exothermic reaction where we break an ionic bond here that takes energy, but we create a lot more energy on the reactant side, on the product side, by making bonds over here. What bonds are we making on the product side that account for that heat being released? Anybody have any ideas?
Covalent?
Nope, they're not. That's a good point. They are not covalent bonds. We talked about them a little bit. Anybody have any ideas? Anyone remember what they might be? What happens with these when they get into water?
Non-polar?
Oh, they're polar. They're very polar. Here, see if this helps jog some people's memories. So here I've got a sodium ion, and then here I've got water. Remember, the water is slightly negative, and the hydrogen is slightly positive. So there's an interaction here. There's an interaction there. Anyone remember what these were called?
Oh, is that a sigma bond?
No, they're like hydrogen bonds, basically. So these are called solvation bonds. We say that the ions are solvated. When they're in solution, they go into a solvent and they become solvated. And so, so you have all these interactions between the oxygen and sodium. And then on the other side, you've got hydrogen, you've got hydroxide, and that's interacting with the hydrogens, which is slightly positive. So you have a whole bunch of waters with their slightly positive side interacting with the hydroxide, and you have a whole bunch of waters with their slightly negative side interacting with the sodium. And it's the formation of those bonds that causes the release of heat. So we're making more bonds than we were breaking, and so we get a release of energy in the form of heat. Okay. All right, let me clear all that. So, so the first thing we need to do with this particular reaction is to write a balanced chemical reaction. That makes sense, right? Whenever we have a reaction, we need to write it out and then balance it. So what is our chemical reaction here? We've got HCl and we're adding it to NaOH. So what, I'll just write that down. So I've got HCl and I'm adding that to NaOH. And then what am I making when I do that?
Is it NaCl plus H2O?
Mm-hmm. So NaCl plus H2O. So is that balanced?
Mm,
Yes.
Yeah, it is, right? But so the actual chemical reaction, so if we were to take into consideration what the states of everything actually is, this wouldn't be accurate. Let me clear that. Because when we have a solution, we have a strong acid and we have a strong base. Both HCl is a strong acid and NaOH is a strong base. Now, what does that mean? If I have a solution of a strong acid, what does that mean? Anyone tell me what that is? Do I actually have HCl in solution? What do I have? Do I have one species of HCl or do I have something else?
You have a mixture.
Not really. What I'm getting at is that, do I have this? Do I have HCl liquid? Is that what I have? What do I have? I don't actually have that, do I?
No, you have aqueous.
It's aqueous, exactly. But what does that mean? So it's not a liquid, it's actually aqueous.
So you have H plus Cl minus.
Exactly. Very good. So yeah, so that means this is what I actually have. And since it's a strong acid, all of this, I don't have any HCl staying together. All of it has been split into H plus and Cl minus. Now, if it's a weak acid, like acetic acid, only a tiny, tiny amount of it gets released as H plus. That's what makes it a weak acid. Because remember, the pH is a measure of the concentration of H plus. And so the higher the concentration of H plus, the lower pH is. So if I have a really high concentration of H plus, pH is very low, I have a very acidic solution. So if I have the same concentration of a weak acid and a strong acid, the strong acid is going to have a much lower pH and be much more acidic than the weak acid is, because all of the strong acid will get turned into H plus, or the weak acid, only a very, very, very small amount of it will. And so that's why acetic acid is much, much less strong than HCl. So if HCl is H plus and Cl minus, what do you think NaOH is?
It's also an aqueous, so it has Na plus OH minus.
Exactly. Very good. Yes. So the same is true for NaOH. So when I take NaOH solid plus water, my reaction is Na plus aqueous plus OH minus aqueous. And that releases energy. So here, in my reaction here, I have a solution of H plus and Cl minus and Na plus and OH minus, all aqueous. And with my reaction, just clear all this. Here is my reaction. I've got H plus aqueous plus Cl minus aqueous plus Na plus aqueous plus OH minus aqueous. Now, what I'm going to get at the end is basically H2O plus this and this. They're going to stay the same. So what do we call those? If they stay the same, if we have an ion that stays the same on one side of the equation and the other side of the equation. You remember? We've got Na plus and Cl minus on both sides of the equation. So they don't actually do anything. But remember what we call them?
Spectator ions.
Spectator ions, excellent. Yeah, so we can actually take these out because they don't really do anything. And so our net ionic equation is H plus OH minus goes to water. And so that is our net ionic equation. And so here, delta H neutralization here, we want to know the delta H neutralization reaction. And so the amount of heat involved with this reaction will equal our delta H neutralization, okay? Because this is the actual reaction that takes place, is this. Na plus isn't involved, and Cl minus isn't involved. So the reaction that actually occurs is H plus and OH minus coming together to neutralize each other and form water. And so whatever heat is involved with that is our delta H neutralization. So now we need to calculate what that is, okay? So let's start doing that. So what is our calorimetry data up here? We've got 50 mils of a half molar HCl solution, and we have 50 mils of a half molar sodium hydroxide solution. So we need to figure out how much that is. And it goes from 25 degrees C to 28.2 degrees C. So let's figure out how much heat that is, okay? Just, oops, go up a little bit. So what is the delta? So basically we have 50 mils, right? We have 50 mils of one and we have 50 mils of the other. So to figure out Q, you need to figure out Q first, right? So what is the Q reaction? Basically, how much heat goes into the solution. So we need to know what is the mass of our solution. We figure out what the mass of that solution. Remember, it's going to be an estimate. It's not going to be precise. If we had to guess at what the mass of the solution is, if we have 100 mils of solution and it's aqueous, it's water, what do we think the mass is going to be?
Would it be 100 grams? Because 1 gram is
right. 1 gram of water
is equivalent to 1 gram.
1 gram.
1 milliliter, right?
1 milliliter, exactly. Yeah. So the mass of 1 milliliter of water is 1 gram. And so remember, this is not going to be precise. It's not going to be exact because we've got HCl and we've got NaOH in there. They're going to add something to the mass too. So unless I give you the density of the solution, you're just going to have to go with water. And that's generally a pretty good assumption, because the density of like a 1 molar solution is not going to be a whole hell of a lot more than water. If you get up to like a 5 or 10 molar solution, that's a lot. So it's probably going to change the density somewhat. But for a fairly dilute solution, 1 gram per mil is pretty good. So how do we calculate Q? What are the 3 things we need to know to calculate Q? Based on your calorimetry experience, now that you're all experienced calorimeters.
Mass,
Mm-hmm.
delta T,
What else?
and
C.
C. Yeah, I forgot
C.
what C
All right.
was, but
So here's our mass. So we're assuming it's 100 grams. What's our delta T?
Change in temperature.
Mm-hmm.
I
So
think
what
that's
is it? 3.2.
Celsius.
Well, 3.2 Celsius and 3.2 Kelvin are the same if it's a change. Remember the change in temperature of one and the other is exactly the same if it's a change. If I increase 1 degree C, I also go up 1 K. It's just where they start and where they finish is different. But each degree difference is exactly the same. So I could have 3.2 C, I could put 3.2 K, it doesn't matter. But since we're scientists, we're going to deal with K. So I've got my mass, I've got my change in temperature, and C. What is C?
Specific heat capacity.
Right. So what do we use for specific heat capacity here? Where's the reaction taking place?
It says to assume the mixture has a specific heat capacity and density equal to water. So would it be 4.184?
Exactly. Good job. Yeah, because it's an aqueous solution, whatever heat that goes into the aqueous solution, that heat's going into water generally. Because 99.99% of the molecules in that solution are water. And so if the temperature of the solution goes up by 3.2 degrees, that's water that's being heated for the most part. So yeah, so we just use the heat capacity of water. 4.184 joules per gram per Kelvin. Now make sure that, so we've got grams on top, we have grams on the bottom, and we have Kelvin on top, and we have Kelvin on bottom. So we should be left with joules. So how many joules is that?
$920.48.
It's not what I got. 100 times 2 times 4.184, right?
Yeah, I got 1,338.88.
Yeah. So it's got to be more than 900, right? Because we're multiplying 100 by 3 and then multiplying that by 4. So
I messed up a number.
okay. Okay, yeah, I got 1339. I got so 1,339. Gotta stop making my 9s look like grams.
Yeah, I was confused about that at first too.
9. There we go. Joules. But we're not done, because if you're asked for like delta H of a reaction or for delta H neutralization, basically, what that means is per mole, okay? And if you remember, our net ionic equation was H plus OH minus goes to water. That's the neutral, that's the actual reaction that's taking place. So we have to calculate how many moles of water are produced? Because right now we don't know. We haven't calculated it. What we do know is that, oh, one other thing I want to ask. Q reaction, is it positive or negative?
Negative.
Exactly. Very good. Yes, it's an exothermic reaction. So if my water goes up in temperature, that heat had to come from somewhere. It came from the reaction. And so that reaction lost that energy into the surroundings, and so it's negative. So I'm just going to write that down. So I've got negative 1339 joules. Now, in order to get moles, we need to figure out how many moles of water were produced. So let me come back up. So I've got 50 mils of half molar HCl and 50 mils of half molar NaOH. So I need to figure out from my equation, how many moles of water is that going to make? And so since my reaction is, since my reaction is 1 mole of H plus 1 mole of OH minus makes 1 mole of water, basically all I need to do is figure out which one of these two is limiting, right? Because that limits the amount of water I'm going to make. But I look and I see that they're exactly the same. I have the same volume, the same concentration of each one. So I have exactly the same number of moles of H plus and OH minus. So really all I need to do is figure out how many moles of either one do I have. So how many moles of either H plus or OH minus do I have here? How would you calculate that? I've got volume, H plus, and I've got concentration, H plus. If I multiply those two, what does that give me?
Your mass?
Nope. What are the,
For
what are the units of concentration?
Moles per liter.
Right. Because you have capital M. Capital N stands for moles per liter. So I have 50 milliliters times 1/2 moles for every liter. So I've got mils and I've got liters. That's not going to work. So I need to convert my milliliters to liters. So how am I going to do that? How do I go from milliliters to liters?
Multiply 50 ml to 1 liter over 1,000 ml. Wait.
No, you're absolutely right. So I would take 1 liter over 1,000 mils, multiply that by 50 mils, and then multiply that by 0.5 moles per liter. Now, I cross out my mils, and I cross out my liters. I got liters here and liters here, and I'm left with moles. So it's 50 divided by 1,000 times 0.5. How many moles is that?
I got 0.025.
Yes, 0.025 moles. So what we figured out so far is that when 0.025 moles of H plus and 0.025 moles of OH minus come together, neutralize, they form 0.025 moles of water, right? Because I have a 1 to 1 to 1 ratio, right? And all of them should be 0.025 moles. So how much heat gets released when I make 0.025 moles of water? We just calculated that a little while ago. Remember we calculated how much heat was released when we did this reaction? How much was it?
Would you multiply that number by the number of moles that we just found for water?
What number did we just find? What was the number of joules released?
1,338.88.
Right. So at 1,339 joules, damn it, I did it again. I'm making that G. 9, there we go. So when we calculate delta H for a reaction, delta H neutralization, remember I said that's per mole. So so when I calculate delta H neutralization, it's going to be in joules per mole. So how do I get from minus 1339 joules and 0.025 moles? How do I put those together for joules per mole?
Divide.
Right, yeah, because it's joules per mole, right? So for this small amount of moles that we made, not very much, we released this much heat, 1339 joules. So if we produced a whole mole of water, which would be a lot more, the amount of heat release should be a lot more, right? We want it in joules per mole. So yeah, so we would multiply this by 1 over 0.025 moles. What does that give us?
I got 53,560.
Right. So let me write. So yes. So that would be our delta H. Let me just erase some of this. That would be our delta H neutralization. Let's erase some of this. So we get an answer of 53,560 joules per mole. What would be an easier way of writing that so we didn't have quite so many zeros? We didn't want, instead of joules, we just wanted like kilojoules, so we'd have a smaller number. What would be the number of kilojoules?
It's 53.56 kilojoules.
Right, we divide this by 1,000, right? And so, and then how many significant digits would we have? Should we have?
3.
3, right, because there's 0.500 has 3, 25.0 has 3, 28.2 has 3, 50.0 mils has 3, so 3. So what would be my final answer in kilojoules per mole?
53.6.
Here you go.
Is it negative or positive?
Negative. 53.6 kilojoules per mole. Yeah, negative because it's an exothermic reaction. So our heat of neutralization will be negative. Okay, so everyone have this down? So just leave it up for a second. So yeah, one thing to remember if you're asked for a delta H of a reaction, it's always per mole, unless, because if it isn't, then it's just Q. Then you're just calculating Q for a reaction. If I put like so much, if I put so much of this reactant and this reactant, and I throw them together, and I don't really care how much product is being made. I just want to measure the heat, then that's Q. On the other hand, if I want delta H of a reaction, I need to be able to compare my delta H of a reaction to a delta H somebody else calculated, to a delta H that's been published somewhere. And so when you're looking up the delta H of a reaction online, delta H means per mole. So everyone has the same number to compare. If everyone's using different amounts, if someone else uses twice as much HCl and twice as much NaOH, when they calculate Q, it's going to be twice as high. But their delta H reaction should be exactly the same. And that's actually something I want you guys to do in your lab on Thursday, is to run through the reaction once with a certain amount of HCl and NaOH, and then double everything. And you should get the same delta H reaction. Your Q should be different, but your delta H should always be the same. Does that make sense? That's why we say delta H rather than Q for a reaction. It means something different. Now that I've just confused the hell out of everybody. Does that make sense? Delta H is a very specific meaning. It means per mole of reaction. Okay, I'm going to clear this. And I'm going to do one more and then answer some questions. Here we go. Because the rest of these you should be able to do. Next one you're not, because we haven't really got to it yet. So the rest of them basically are Hess's law questions. We haven't gotten to that in lecture yet. So what I'll do is we can do this one, and then I'll show you how it works. And then after the lecture, you'll have a week, to do this. So don't worry about finishing up. But I just sort of basically wanted to show you how Hess's law works, because I don't know, I think it's fun. Basically, what Hess's law is that you can calculate the delta H of any reaction if you can figure out what internal steps are in that reaction. In other words, if I can go from step A to B to C to D to E, and I can calculate every one of those steps, then I know what the reaction of A to E is without even doing the reaction. I can just calculate it. So if I have, in other words, I can make it even more complicated. In other words, if this is my reaction here, I want to be able to figure out how I can get to this reaction with all of these reactions over here. So these reactions, the delta H reaction has been calculated for each one. Is there a way I can rearrange these reactions? I can add them and I can subtract them. And to get to this at the end. So basically what you're going to be doing is either just looking at the reaction, you can flip it. And when you flip it, you flip the sign of the delta H. I'll give you an example. So what you want to do with these reactions here is arrange them so that you have these reactants on the left side and the products on the right side. So in other words, we will look and see which one of these reactants has our products and which one has our reactants. And you look at the first one, NO plus ozone, O3, gives you NO2 plus O2. You look at that and you feel, okay, I've got O2 as a reactant, or NO as a reactant, and I've got NO2 as a product. So that's going in the right direction. We're going to leave that one alone. Then I go down to the next one. It's got ozone on one side, it's got O2 on the other side. And then I look at my reaction, it hasn't got either one of those things. So I don't know what to do with that yet. So I'll skip that and go to the next one. Next one has O2 goes to 2 atoms of oxygen. I look at that, say, oh, okay, I've got an atom of oxygen. Let me change colors for a sec. I've got an atom of oxygen in my reactants. Here, though, I've got 2 atoms of oxygen as products. So what I'm going to have to do is flip that reaction around. So I have atoms of oxygen on the left side as a reactant and O2 as a product. And when I do that, this flips. It goes from being plus 495
Negative.
minus 495. Because if a reaction is exothermic going in one direction, the reverse reaction is endothermic, right? Just like if you have ice. If I have a ice cube in my hand and it's melting, that's an endothermic reaction, right? Because heat from my hand is going into the ice and melting it. Now, the exact opposite reaction is exothermic. You may not think it sounds kind of strange, but when you put water in the freezer to freeze, that's actually an exothermic reaction because heat is being taken away from the water and going into the freezer, where then it's cooled in the back of your freezer and then returned. And so that's actually an exothermic reaction. Heat is being lost from the liquid water and it's being turned into solid water. So it's exothermic in one direction and it's endothermic in the other direction. And the same thing here. What we're going to do is rearrange these 3 reactions until when we add them all together, we get exactly NO plus O gives NO2. So right now, I'm going to cross this one out because we've changed this one. So let's see what we've got so far. I've got 2O on one side. I've got O2 on the other side. I've got ozone on the left as a reactant, and I've got O2 on the right. So if I added all these up right now, they wouldn't add up, right? So looks like we need to do something with this one. Looks like we're going to need to do something with this reaction in order to get everything to balance out. Because right now, if I just added all these together, I would have NO plus O3 plus 2O3 plus 2O gives me, and then I add everything on the right side, NO2 plus O2 plus 3O2 plus O2 again. So I have a lot of oxygen in this side, and I have a lot of ozone in this side. And you'll see from my reaction up here, I don't have any oxygen or ozone in it. So I need to do something with this reaction in the middle to get rid of all of these. So what do you think I can do? Anybody have any ideas? What if I was to flip it? What if I was to flip this one? If I flip this second equation around, let me just erase, oops. Just erase these. If I flip the second one around, then change color. So if I flip the second one around, I've got 3 oxygens goes to 2 ozones. And now my delta H is flipped also, and it is now positive. So the delta H for this reaction is plus 284.6 kilojoules. Now let's try, so again, now I'm going to cross this one out. Now let's add them all together and see what we get. So remember, you add everything on the left side, all the reactants get added together, all the products get added together. And let's see what we get. So we have, again, NO plus O3 plus 2O plus 3O2 makes NO2 plus O2 plus O2 again plus 2O3. Now we add these together. I've got O2, O2, O2. That leaves me with 1 oxygen over here. I've got O3, O3, leaving me with 1 O3 over here. And NO2, NO, 2 oxygen. So basically, I just need to account for this oxygen and this ozone. Ozone? It's good to have a really big piece of paper when you're doing these. All right. 2O. Let me try that again. My terrible handwriting is, oops. Let me try that again. Just want to make sure I've got these reactions right. Okay. All right, NO, O3, NO2, O2, okay. Add them. And NO plus O3 plus 2O plus 3O2 NO2 plus O2 plus O2 plus 3. So that leaves me with a net of 1. So if I have 2 oxygens on this side and 1 on this side, that leaves me with 1 on this side. I've got 2. So I've got a net of 1 ozone on this side. Oops. So I need to do something with my Yeah, obviously I need more time with this this particular one.
Yeah, this looks pretty confusing.
It is.
I kind of lost you a little bit.
Yeah, I got lost myself. So yeah. Obviously I didn't go through this first.
I have a question. Like, are we solving this like math, like system of equation, like to eliminate the ozone?
Yeah, exactly. Yeah. So actually, if you guys wanted to work on number, oops, clear this. I'll come back to it. If you want to work,
When I do it, like I kind of have like a real result. So what if
you
like I have a
you
minus sign?
you got it figured out already?
Like I'm
Did
not
you
sure
manage
if
to
it's
solve it?
correct. Yeah, I did, but I'm not sure if it is correct or not. But I have like a
Okay.
minus sign in front of an element. Like I have 2NO, and then the
So you doubled it. Oh, that makes sense. Yeah. Yeah, you can also
I actually like
multiply and divide these as well.
I multiplied the top equation by 2,
Mm-hmm.
and then
Okay.
multiply the second equation by -1, so that I can eliminate ozone. But then I end up having minus O2 on the result.
Well, you can't have like a minus. You can't multiply. But if you multiply by -1, that basically means you're just flipping it from one side to the other. So if you mean by if you multiply the second one, let me get my. If you multiply this by -1, all that means is that you're changing the direction of the reaction. You're just changing it to go from forming O2 to breaking down O2.
Yeah.
Yeah, I just need more time with this one. Actually, I didn't even check to see if it does work. I should have checked that first. Anyway, but if so, what I will do is, you guys want to take time, work on a different question. I'll take like 5 or 10 minutes to work this out and then come back to it. Okay. If you have any other question about any of the other ones, you should be able to do fairly easily, hopefully. But yeah, so yeah, we did 4, and 3. So like basically 1 is the only one you really need to be able to do, and you can do that one. I could 6 or 7. Just gonna, yeah, give me like 5 minutes. I'm going to work on this one, okay? And I'll come back to you. pause. There we go. Okay. So, and flip these around. I could basically do anything, any sort of mathematical change I want to do. I can do that. It's perfectly fine. But whatever I do to the reactants and the products, I have to do to the heat as well. All right. So this was a little tricky because I'm not very bright in picking something easy. So here we go. So at the end of the day, we want to come up with this reaction here. And we can use any tricks in the book to flip these three reactions. We got 1, 2, 3. I can do anything I want to those. So when I add them up, I add all the reactants from all the reactions. So I would add everything on this side of the, these are all reactants and these are all products on this side. So I add them all together. And at the end, I want to come up with this. Okay, this one right here. And then, so whatever I do to those reactions to get them to add up, I have to take that into consideration with the heat. So what I'm going to do is, let's start with, since I started with something really easy. What you need to do is to multiply this first one by 2. So whoever had that example, they were right. Very good on you. You multiply the first one by 2. It doesn't appear to be obvious that you would need to do that because you have 1 mole of NO and you have 1 mole of NO2. Why would you want to multiply it by 2? But you'll see that you need to do that in a second. So I have 2 NO plus 2 O3 gives me 2 NO2 plus 2 moles of oxygen. So remember, you have to multiply everything in it by 2, including the heat. So basically what that means is if 1 mole of reactions makes this much heat, then 2 moles of reactions has to make twice as much. Okay, so we would take the minus 198.9 and multiply that by 2. So that gives us minus 397.8 minus, because it's twice as much stuff. So for the second one, I have ozone on the left as a reactant, and I've got O2 on the right as a product. And what I'm going to want to do is flip that around, okay? So what I'm going to have is 3O2 makes 2 ozones. And since I've done that, I need to flip this as well. And so that would be plus 284.6, okay? And then finally, bottom, I've got oxygen makes 2 atoms of O2, oxygen molecule makes 2 atoms of oxygen. And I'm going to want to flip that because I want atoms of oxygen as a reactant, okay? So I'm going to flip that around. So 2O makes O2. So since I flipped that, I also need to flip, oops, it goes from positive to a negative. So that is negative 495. Now, when I add all of these up, let's add them together. So I've got, let's cross out what is present on both sides. So I've got 2 moles of ozone here. I've got 2 moles of ozone here. So since they're a reactant and a product, I can cross them out, okay? We would call that an intermediate. Means it's produced in the reaction, then it's consumed in the reaction. So basically it was like it was never there. So next I have, how many oxygens do I have? I have 2 here. I have another one here for a total of 3 oxygens as products. And I have 3 oxygens as reactants too. So I have 3 O2 as a reactant, and I have 3 O2 as a product. Therefore, I can cancel all of them. All gone. And those would be an intermediate as well. And what am I left with? I'm left with 2NO
It's 202.
plus 2O gives us 2NO2. And I add all of my heats together. So it would be minus 397.8 and minus 495. Oops. 397.8, 495. 4, 6. So my total is minus 608.2 kilojoules. Okay? But am I done?
You need to divide it by 2.
Exactly. That was the really tricky part of this whole thing, was that, yeah, you had to multiply by 2 and then divide by 2 at the end. So this would be like a bonus question on an exam. So yeah, this one's really super tricky. So at the end, I would just, yeah, divide by 2. And so this becomes 1. So that becomes 1, that becomes 1, that becomes 1. And then I would divide the 608.2 by 2. So I get 304.1. And so my final answer would be negative 304.2 kilojoules. So you can see we can calculate the enthalpy change for this reaction and not even do the reaction, because we know what the enthalpy changes are for all these other reactions. And so as long as we can add them together in some way that we get the NO plus O equals NO2 at the end, we can figure out what the enthalpy of that reaction is. So using Hess's law, we can figure out what the enthalpy change is for reactions that are almost impossible to do. But if you add a number of different reactions that are possible to do, you can get to the impossible reaction and figure out what the enthalpy change would be. So yeah, sorry for making that one so mind-bendingly difficult. Yeah, that's a little advanced for the very first one out of the gate. I hope I didn't lose everybody there.
I have a question.
Yeah,
Yeah.
same here.
Okay.
So for the first delta H, isn't it supposed to be so I was wondering, where did you get minus 397.8?
Oh, because I multiplied that first reaction by 2.
2. Oh, so like if you want to,
So I multiply the heat by 2.
so if you want to like divide, like let's say divide everything by 2, so you divide the heat.
Divide the heat by 2. That's perfectly fine.
Okay.
Yeah, and so you'll find in a lot of these, you get these really weird reactions, like this first, like the third one here, I could have divided that by 2 and then have like half. Could have done the same thing. I could have like divided the second one by 2 and the third one by 2. And so I would have had something like half a mole of O2 makes 1 mole of oxygen atoms. That's perfectly fine. And then my delta H would be half that. So you could also do it that way. Instead of multiplying the first one by 2, you could divide the other 2 by 2. Basically, you get the same answer, just a different way of getting there. But what you can divide it by 3, you can divide it by 7 if you want. So you get all these weird numbers. Like you can have like, you you shouldn't, if you to write down a chemical equation, you shouldn't have like, you know, half a molecule of something, because there's no such thing as a half a molecule of something. But here we're dealing with moles, and you can easily have like half a mole of oxygen molecules, or half a mole of oxygen atoms. That's totally fine, because we're dealing with the energy. We're trying to calculate the energy for a reaction. So that's perfectly legitimate to do. We don't have to have whole numbers here.
And I had a question about what's it called? How you got to the what's it called? The calculations. How like the first one you multiplied it by 2, the second, third one you just flip the signs. Like what makes you do that? I didn't quite understand that part.
Oh, it's just no. It's just how I sort of figured that out was I realized that you needed to have an odd number of oxygens and ozones in order to make this work.
Mm-hmm.
And so the simplest way to get to that was just to multiply the first one by 2. That was just the easiest way. That was the way to get like 3 oxygens on one side and 3 oxygens on the other, and 3 ozones on one side and 3 ozones on the other. The way to do that was to multiply the first one by 2.
Oh, okay.
That was it. Yeah, that was the tricky part. Because like, yeah, the first time I'm looking at it, you're like, how the hell is this going to work? Because there was just these odd numbers, and so yeah, you had to multiply or divide something to get to the right number. But yeah,
Okay.
the ones we'll do in class that will be easier than this. For some reason, yeah, this I found this somewhere, and yeah, I forgot that it was really hard to do.
Okay, just wondering.
But hey, if you can do this one, the rest of them will be gravy, right?
Sure.
Yeah, kind of. Just the only thing that gets me is the figuring out what to do. But I
So
understand what you're saying.
that's why I find these are fun. They're kind of like puzzles. Like you just sit down with them, and it's not just a straightforward calculation. You get to play with them. You get to flip them around and multiply and divide them, and then when you get them, it's like, oh, cool. So if you like doing puzzles, you like doing these. If you don't like doing puzzles, you're going to hate them. So you guys better like doing puzzles. Is all I'm saying.
I'm more of a Sudoku guy.
Well, it's kind of like Sudoku. You got to fit things together in Sudoku to form a pattern. It's the same thing here.
I have one more question.
Yeah.
So when you add all the 3 equations together, and we're supposed to have like 2NO plus 2O and 2NO2 on the result, right?
Mm-hmm.
So when we eliminate the 2 by divided by 2, so isn't that delta H supposed to be divided by 2?
Yes.
So it's going to be minus 300.
Exactly right.
Right?
Yes. So the final answer is not that. The final answer is half that. So was it 300 and
4.1.
304.1. Yeah. Yeah, that'd be the final answer. But yeah, so yeah, I'll give some more of these to do. We'll do some more of them in class. But yeah, I don't know. I just find them fun. I don't know, it makes me a bad person or whatever. I just like doing them.
And what did you say the rest of the recitation was?
Oh, so we'll deal with the rest. I mean, the next one is basically, the next question is basically the same sort of thing. Oops. The next one is it's basically the same question, same kind of question. Use the combust. Actually, I'll just show you the outline of how to get started on it. Okay, and then you can, because basically the only difference between this question in the last one, is that you have to figure out what the chemical equation is. And so here it says use the combustion of methanol to calculate the heat of formation of liquid methanol. Now the heat of formation is basically, so the reaction for the heat of formation would be C plus, oh, wait a minute, 1/2 O2 plus 2H2 makes CH3OH. Now the heat of formation means forming a molecule from the most stablest form of all the other atoms that are in there. So CH3OH is methanol. So it has 1 mole of carbon atoms, it has 1 mole of oxygen atoms, and it has 4 moles of hydrogen atoms. So from the most stable form of all those compounds, you have graphite, solid, you have O2 gas, and H2 gas. And the heat of formation of all of these is 0, 0, and 0. And so the amount of heat it takes to make this, you can calculate using all these reactions. So the first reaction you have to calculate, you have to come up with yourself, which is the combustion of methanol. Now the combustion of methanol is CH3OH plus O2, right? I mean, combustion is just combining with O2 and making water and CO2. Then we have to balance it. So I've got 1 carbon, 1 carbon. I've got 3 oxygens, I got 3 oxygens. I've got 4 hydrogens. Oops, I've only got 2 over here. So I need to put a 2. Need to put a 2 there to balance my hydrogens. Now I have an odd number of oxygens. I've got 1, 3 on one side, and I've got 4 on the other side. So what I'll do is just put 3/2 oxygens here. So that will give me 4 oxygens, 4 oxygens, and everything else is balanced. Okay, so I use this reaction, this one right here, plus this one, plus this one, plus this one, to give me this at the bottom. So, and then you can, so you want to figure out what the heat is, what's the heat of this reaction? And so you have the heat, it gives you the heat of this one, the heat of the combustion reaction is 726.6. The heat of formation is CO2 is minus 393, of water is minus 285. And this is, oh, actually it was written out for you. I didn't even notice that. Yeah, so the heat of formation is the last equation there, which thankfully I got right. So you take these first 3 reactions and you flip them and you turn them around every other way to try and get the last one, okay? So I'll leave you with that to try and figure out. And then, I don't know, maybe on Thursday, if we have some time after class, I'll go over it. But yeah, have some fun with that one. So do you have a pretty good idea how to attack that one? So take the first 3 reactions and try to arrange them to get the 4th.
Which one is like the final equation that we want?
The final equation you want is this one. You want to, oops, you want to end up with this.
Oh, okay, okay.
So this is your first reaction, this is your second one, and this is your third one. So you want to flip them around, divide, multiply, do whatever you need to do,
Oh, so the first one is that we have
and
to
then
come
end up with
ourselves.
that.
Oh, okay.
You need to get the whole reaction or equation to look like that, or just like the products and the reactants?
At the end, you're going to add up all your reactions. And if you have the same thing on both sides, if you have, like, let's say you've got, 3 waters on one side and 2 waters on the other side, you eliminate these 2, and then this becomes 1. So basically, if you simplify them down, and if you have, like, 2 oxygens on one side and 2 oxygens on the other side, you just cancel them. And then by the end of it, when you add them all together, you should end up with 1 mole of carbon, half a mole of oxygen, 2 moles of hydrogen as reactants on the left side. And on the right side, the only thing you should have is CH3OH. So I would probably recommend that you flip the first one. Because basically combustion is, pretty much the opposite of formation, right? And you're taking something that's already formed and you're blowing it up. So generally, when that's your first equation, you should usually just flip that one around, because it gets you your methanol on the product side, which is what you want. So that's my first hint to you. Is you're going to have to flip the first one, I would bet, and then the rest you're on your own for a little while. Any other questions before we call it a day? Everyone's just scratching their head. It'll hopefully.
Yeah, I'll try.
Hopefully it'll come into make a little more sense on Thursday. We go into this in class. I'll have a little easier examples than these, but you don't want them to be easy. What would be the fun in that?
And when is this due?
Week from Thursday. Or week from today. Sorry, week from today.
Okay. And as for lab, which lab are we doing on Thursday?
Number 10. It's under the online lab on the Canvas.
Okay.
I just posted it this morning.
So are we doing the lab, the pre-lab for it? Because I know you said something about that.
No pre-labs. Just the lab reports. I'm going to have the lab reports worth 20, and then there won't be a pre-lab. Just do the lab, write a report.
Okay.
All right. Thanks again.
If there's any other questions, just feel free to email me, or if you want to set up a sort of virtual office hours, I can do that too. Okay, I've already done that for a couple students that I really don't mind. Or I should have the same office hours as I normally did, but nobody ever came to them. So I'm just making it more flexible. You can have them whenever you like. I mean, we're going to be home for a while, right? Okay, so I've left you with some exploded brains. Feel pretty good about that. So we'll see you on Thursday, unless I see you sooner. Okay?
Can I have one more question?
Of course.
Regarding the conversion for the question number 2.
Number 2, okay.
For the specific heat capacity of the calorimeter, like if I wanted to convert it from joule per Kelvin to joule per Celsius, how do I do that? Because like the Kelvin to Celsius is not, its conversion is not like multiplying. It's at 273. So like when I convert it, like I don't know how to convert it.
You don't have to worry about converting it. That's the cool thing, because let's look at this. So what's the freezing point of water in Celsius?
0.
0. And what's the boiling point of water in Celsius?
100.
100. What's delta T between those two?
100?
100. Now in Kelvin, what's the freezing point of water?
I understand that like the difference is the same,
Yeah,
but when we like substitute it into the formula, like the equation,
you can substitute them because remember, it's always delta T. We never deal with the temperature.
so then if I use the joule per Kelvin for the heat capacity of calorimeter, which means that I have to use joule per gram Kelvin for the heat capacity of water, right? Then I
Yeah,
will
it's
have
just, it's the same. The heat capacity of water is 4.184
yeah, but it's in
per gram Kelvin. And it's also 4.184 joules per gram degree Celsius because
oh,
we're only measuring the delta T. We're never, because all of these equations, Q, remember Q, heat is only involved with the delta T. It's never the temperature. It's always the change in temperature because we're always measuring the change in temperature from one state to another state. Either it's cooling, so that Q is negative, or it's heating up, Q is positive. It's one or the other. And so it's if no temperature change takes place, Q is 0. And so we don't need to deal with it. So heat is it's always delta T. So in this
right.
instance, K and degree C are completely interchangeable.
I got it now.
Yeah.
Oh, so we can say that like if there's no changes in heat, like there's no Q, like
No
literally no
Q.
Q.
Q is 0.
Oh,
Yeah.
okay.
Because remember, Q is the mass times the heat capacity times delta T. And if delta T is 0, it doesn't matter what anything else is. The masses could be anything, the heat capacity could be anything, but Q is 0. Has to be, because the temperature didn't change. Okay?
Oh, okay.
Yeah, that's a good question. Yeah, because I think students get freaked out when they see Kelvin. They go like, oh my God, I'm constantly gonna have to be jumping back and forth. But if it's a change, don't have to worry about it.
Oh, so like it doesn't really matter because the change is gonna be the thing that we're gonna use to multiply with, not the.
Always.
Okay.
Always, yeah, because Q is a function of delta T. Delta H, the change in enthalpy of the reaction, is a function of delta T. If the temperature doesn't change, then there's no Q.
Oh, okay.
Any other questions before we head out?
No.
All right, it was good talking to everybody. Stay well. Remember, if you have any questions, I'll be here. All right, I'll talk to you later. All right, bye everyone.
Bye.